Hi, let's start. Welcome to Build 2015. I'm Gopal Kakivaya. I'm a corporate vice president at Microsoft. Today I'm really excited to talk to you guys about Service Fabric and its architecture. For a great part of my career at Microsoft, I've been working on this technology. I led the conception, incubation, realization, and productization of this technology. We initially built this technology for use by our first-party services. As our first-party services became successful, we thought it's a good idea to make it available to external developers as well. And that actually brings us to this day where we are announcing the availability of this technology. When we actually started working on this technology, what we realized is that many of our first-party services were repeatedly solving the same hard distributed systems problems. And in the process, I think there was not only a bunch of needless work that was getting done, but also that bugs or stuff that was done in one service was not getting leveraged in another service. So we realized that we have an opportunity to really lay a foundational distributed systems platform on which many of the first-party services could build, and that first-party services could leverage and build. And that's how we created this technology. This technology now, I think, is being made available to third parties, and there's an SDK that is available. If you go to the download center, you can actually download the SDK. You can create Service Fabric applications in a really scale minimized single box setup. You can take those same applications that you actually develop on your box and move them to run as is in Azure Cloud when we actually offer this as a hosted service offering in Azure in a couple of months. You can also take the same applications that you're running and move them on premises, because we are going to ship this technology in the upcoming release of Server 2016. So this is a great moment, and I have also one of my colleagues and teammates who is actually going to come on board, come up, and then do some presentations as I do some demos as they come up. Here is the evaluation slide. But here is the agenda of my talk. I'm initially going to talk about how the application development has changed in the cloud world and how Azure Service Fabric actually helps you build cloud-native applications based on the microservices architecture. I'm going to talk briefly about how you can build scalable, reliable, and easily managed microservices using Service Fabric. Talk a little bit about how the system has been put together. I will peek under the hood a little bit and tell you guys the various subsystems which are internally running within a Service Fabric cluster. And how they come together nicely to solve various hard distributed systems problems, so that developers can focus on their service logic instead of the underlying platform aspects. And I will summarize at the end. Not long ago, in fact, it was true for me, it was true for many of my colleagues, like, for example, SQL Server guys, where I also worked. And now I work in Azure, but it was not long ago that we were actually happily developing a bunch of features. We would ship these features every 2 years in a box product, and then cycle used to begin. But that has changed with the advent of the cloud, because now not only are we required, in fact, it is true with our SQL developers today, we are required to not only deliver features, but also we have to take care of a whole bunch of stuff on the right-hand side of this slide. Like, you have to think about how do you build your service so that it is scalable from the get-go. How do you actually solve make sure that the service remains available even in the presence of machine failures, or more importantly, when you're patching that service. How you actually think about how to build scalable, how to build low latency, high throughput applications, and all of these problems. And think about data sovereignty, data backup. You have to think about all these problems, and unfortunately, if you start with the bare metal machines, these problems are right in your face. So would it not be nice for a platform to actually help you with solving these problems, so that we all can get back to actually developing features or service-specific logic that at a faster pace and help with the business agility and provide business value? The cloud. Another thing that has actually changed for us is the fact that the architecture that we are so used to in the past is not the architecture that you use for building cloud-native applications. If you actually go and peek underneath any of our workloads, like Azure DB or DocDB or Cortana, you actually see that they're not actually built in a tiered way at all. They're built in a different way, and the advantage of actually building in a tiered way, or disadvantage if you actually think about it, is that you could build all of these things, you could put all of them in a set of machines, and you actually depended on machines to provide the reliability. You typically ran them on big iron machines. You actually could afford to take some maintenance windows, maybe over the weekend, where you could actually bring down all the pieces of the software, patch them up, and get them ready for the following Monday. But in the cloud world, it's no longer, that's not something that you can do, because if you do that, your customers will flee from your business or from your service. So it is important for you to really think about the right-hand side of this slide, unfortunately, so that you build in a different way so that you get the benefits of the right-hand side by building on top of a platform. And the way you actually think about building cloud-native apps in the modern day is to really decompose the service components into a loosely coupled, interacting over standard protocol microservices. And again, it would be great if the platform actually helped you with that, and that's exactly where Service Fabric comes in. So when you are, in fact, this is true for us, this is going to be true for everybody who's thinking about building high-scale services. When you're building a high-scale service, you really need to think deeply about scale, reliability, and cost. It is important that you design for scale from the get-go. So you want, because the demand for your service is going to be variable. You may start off small and suddenly it may pick up steam and then become very popular. So you want to really design your service such that you can run on a small setup and to a large setup without actually having you go back and revisit the architecture or rebuild the service from scratch again. So how do you do that, I think, is something that you have to pay attention right at the beginning and not think about it as an afterthought after the service has been built or deployed. You also have to think about reliability. You really want to keep your service up and running. You can't afford to have any maintenance windows. You really have to keep the service available even in the presence of failure, not only in the presence of machine failures, but also when you're doing live patching of the service. And obviously, I think cost is very important. Again, as developers, not long ago, we thought, we are developing code and we are writing features, but that's no longer true, because every feature or every piece of code that you write, if it is more expensive to run that piece of code, then we are not doing a good job. So again, we really need to think about how we can use smart software on top of commodity hardware, as opposed to hardware on top of big iron machines, to actually deliver unparalleled reliability and scalability at the best economical value. And these are the problems that our first parties have faced, and we delivered a bunch of technologies for these people, and that's where Service Fabric came in. And it actually, I'm going to talk a little bit about some of the features that Service Fabric provides, but it is for building, so it is for doing the heavy lifting that is necessary for you to really build your services so that they are from get-go, scalable, reliable, and run at the best price that you can think of. Because one of the things that we actually take pride in this particular system is that we have shaved every possible I/O and every possible message in the system so that you get the best price. Obviously, if you build on top of this service, we are shipping on Windows today. You can actually use C, C++, or C# APIs. We are going to make this technology available on Linux, and you can and also expose them via other programming models like Java or JavaScript, so that you have the choice of actually running on the platform of your choice or OS of your choice, and you can also deploy it on Azure, or on premises, or on third-party clouds. So by actually running on top of this platform, you have some choice in how you want to deploy your app or your service. This particular slide is showing the number of first-party services that are running on top of Azure, on top of Service Fabric. It is not that we we conceived this technology or we built this technology last year and we're giving you this technology this year. We have, this technology was conceived more than a decade ago, and this has been running in production underneath all of these services for the last 5 years. More importantly, we are giving you the exact same bits that are underneath these services in this SDK. I will talk about where it is different in a minute, but we are not giving you a different version or less functional version or a different copy of our code. We are giving you guys our code. Bunch of Azure infrastructure itself runs on top of this. If this service fabric doesn't do its job, a bunch of Azure itself goes down. Similarly, the most transactionally consistent databases are running on top of Azure Fabric. We are the people, the Service Fabric is the one which is doing all the heavy lifting of replication, reconfiguration, managing the lifecycle of every individual database that actually you have running in Azure DB today on tens of thousands of machines. It actually is running consumer-grade services which are processing huge amounts of subscriptions in Bing Cortana, and it actually scales across 3 data centers. And recently, they had an entire outage of an entire data center, and the service kept running. And that's because of this technology that they're leveraging. In the next, in the rest of my talk, I'm going to talk about how Service Fabric, I'll peek a little bit under the hood so that you guys can see. I'm sorry, I don't know why this. This thing keeps moving. I'm just going to keep going back and forth. Okay, so basically, I'm going to talk about how the Service Fabric has been put together, its major subsystems, so that you get a little bit of an understanding of how the system works. And along the way, I'm actually going to talk about the exact problems that these different subsystems are going to solve. And hopefully motivate you on the role these subsystems play in the system. Before I actually start talking about the underlying parts of the system, let me first actually talk more precisely what we mean by a microservice. If I'm asked to actually go and design an internet scale service, I'm actually going to not think about the machines. I'm going to think about my problem. I'm going to think about what exact scenarios my service is meant to solve, and actually decompose that problem into a set of entities, and then have those entities. Then I would think about what is the scale characteristics of my service, and I say, oh, this particular entity I want to scale differently than this other entity. So this decomposition is at the core of microservices architecture. You really never think about machines, unlike if you start from bare metal machines or virtual machines. Here, you're thinking more at the app layer, and you're thinking about the app logic. How do I decompose it? How do I make it run in such a way that I can upgrade different parts of my app without actually anybody noticing that I'm doing an upgrade? If you actually go and take a peek underneath Azure DB, there are like 7 or 8 services that are microservices that are running. Obviously, the biggest microservice there that's running is the database service, but there is a protocol gateway which is terminating TDS connections. There is a management endpoint, which is actually, whenever you go and ask for a database in the system, it is the one which actually goes and calls Service Fabric, hey, I want a database, please go and create a database for me. So all these microservices that are running in the system, they're all interacting with one another over well-defined protocols. So what exactly is a microservice? A microservice is a piece of code or a piece of logic with and its associated state. And every microservice in the system has to have a name so that you actually now talk about, hey, where exactly is my microservice is running? You do not talk about which machine it's running. You talk about where is my microservice. So the naming system in Service Fabric actually is responsible for actually determining where exactly a given instance of a microservice is running, so that so that you can go and talk to it. So these microservices remain logically consistent. A database obviously cannot lose its state or not lose its transactional integrity because a bunch of machines failed. It has to remain consistent all the time, and despite machine failures, despite a bunch of upgrades that you actually end up doing. And a microservice obviously doesn't actually appear in the ether. You actually write a bunch of code, and you say, here is the code that is backing this service, and I want you to go and run this particular code. And that code is what we actually put inside a container. When I mean container here, it's more general than the container that we all love and understand. More recently. It could be a process group inside running a job object. In many cases, it's a bunch of processes. There's a SQL Server.exe, there's a watchdog process, there's a bunch of supporting processes. There's a full text indexing engine behind that SQL Server.exe. All these processes are managed as a single entity, and they all may be running inside a container. And typically, each microservice, you want to have a small team of developers responsible for it, and they can move independent of other developers building other services in the larger, internet scale service. So that's why this architecture lends itself to increased agility, better reliability, and better scalability, because you can scale independent parts. You can actually move independent, you can upgrade or downgrade independent parts without, affecting other parts that are dependent on them, because they talk over well-defined protocols. Obviously, there are two types of microservices. A microservice which is stateless, and then a microservice which is stateful. And what exactly is a stateless microservice? A stateless microservice obviously does not maintain any state or important state. It may cache some state. That actually lasts beyond the request and the response that that particular service receives. In the case of TDS protocols, there are some protocols which are stateful in the sense of they have some session state, but most of the protocols that you actually typically know, most of the web front ends or protocol gateways are stateless because they don't maintain any state. And the way you actually achieve reliability for stateless services is by maintaining n copies of them. And actually, this is not there's a hard problem here from a distributed systems point of view, but this is what actually everybody tells you. Hey, in order to achieve scale, just go and build stateless services. But who's going to solve the stateful problem? Obviously, I think when we were building the system, we were actually thinking that this particular problem has to be solved by us, because we are the people who are actually supporting the database technology, which is stateful, at the core. So for stateful microservice, on the other hand, you have state that actually lasts beyond a request and a response, and that state is authoritative. You cannot afford to lose that state. There has to be a kernel of truth somewhere, because if everything in the entire world is stateless, you have nothing in the world, because you have to have some amount of state lying around somewhere. So who's maintaining that state? That's where these stateful microservices actually come into play. And the way you actually achieve reliability for stateful microservices is by maintaining n copies of that state. Obviously, you want to maintain those n copies of the state in a consistent manner, because you really have to think about how you're updating or mutating that state. And the system has to give you those guarantees that the n copies of state you're maintaining are indeed consistent. And how I'll talk about a little bit about how we achieve that consistency. And example stateful microservices are databases and documents and user state, user profile stores, and other things. So with that in mind, I'm going to invite my friend and my teammate to come on board and actually talk about a stateless microservice, because I'm now taking you guys on a journey of making how the system starts off with a simple thing and how it becomes complex as you go down the path. In this particular case, it is a stateless microservice. It's nothing but a visual object which is freely moving in space. It does have state, and that state is a location it is in, and the past 10 locations where it had been. And we will show you how that stateless microservices show it running, and we will induce some failures and see where it goes.
Hello, everyone. So here is an example of a stateless microservice. In this case, the microservice is an object floating around in the space. The state of that is represented by the current position as well as the history, which is represented by the tail. Here is a Service Fabric Explorer. This is a tool that we offer as part of the SDK, which allows you to visualize, manage, and monitor your cluster. What I'm going to do is that here I have that service, which is the stateless service. That stateless service has one instance, and it is running on node 3, as you can see here. So I'm going to put this to auto refresh. And so we have one instance of that service running on node 3. And what I'm going to do is basically restart node 3. So watch what happens to the instance that is here as well as the object. So as you can see that.
In this particular case, actually what Vipul did is that he just took away a machine. Think of it like that. When that machine failed, the system actually detected the machine has failed, and it actually is going to figure out where to place, realize that this particular microservice has failed, and it's going to restart that microservice on a different machine. You'll
see it come up.
You can see that it actually came back, but unfortunately, I had to put on my glasses because I'm getting old. What I think maybe you guys didn't notice is that when it actually restarted on a machine, this particular microservice lost its state. It lost the position it had been in, and the last 10 positions it had been in. So it actually went back to some, the position where it actually took life or took birth. Because let me go back to my slides. Yep. So, but the system did solve the problem of detecting that the machine has gone down and actually figuring out a particular instance of a microservice has failed and directing it somewhere else. How did it do that? And that's where the failure detection problem for the system comes. Even for stateless microservices, which we think are the easy ones compared to the stateful ones, there is a hard distributed systems problem, which is a failure detection problem. And that's what these two subsystems actually provide in Service Fabric. Obviously, we have a transport, which is, if you are building any distributed system, you have to have machines talking to one another. All of this is not running on a single machine. So how do we actually have this communication established between machines? We obviously use this thing called transport. It's, it has lots of security. It does a bunch of stuff. But at the end of the day, that's actually not that hard, other than making sure that it is secure. It uses Kerberos and a bunch of other stuff. The more important characteristic it has is that it is best effort. It doesn't actually give you any guarantee to the layers above it that it is going to deliver the message. We could have easily used TCP, UDP, though we use TCP in our Service Fabric at the moment. The reason we use TCP is because we get fragmentation and reassembly easily, because TCP does that for us. And more importantly, we get the TCP offload. I don't know whether you guys realize that in modern chips, particularly unless the messages are very, very small that you can actually fit in a single frame, it is actually more faster or more performant to actually run TCP than UDP. Of course, there are special cases like broadcast and other things where UDP is useful, but in a typical data center network, TCP actually performs very well because you have TCP offloads, checksum offloads, and a bunch of stuff that you actually can benefit from. On top of that layer, the best effort layer is what we call the federation. This is where I will introduce the notion of a cluster. So in absence of federation, what you see in a data center, in fact, if you don't have Service Fabric, this is what you get in Azure, or for that matter, any other data center. You go and ask for a bunch of machines. You get a bunch of machines. What can you do with these machines? Let me start and let me build this. Oh, how do I know about this machine being part of the system? Oh, how did this machine fail? All of these problems are in front of you, and we don't know how to solve. And every developer starts from the bottom of the stack and tries. So in other words, just having a bunch of machines with the great OS that you love is not enough to build a service. You really need higher level abstractions and higher level platforms on which you can actually build your service specific logic so that you do not have to go and solve any of these problems. Not only that, you actually never think. Most of our developers do not think about machines. They think about their code, their packages, how many instances of their code needs to run, and how can they maintain state reliably. And that's what our services use, and that's what we are making available. So what happens is that when the Service Fabric cluster comes up, it basically goes and determines what machines are part of the cluster, and then at this point of time, it knows what machines are in the system and what machines have failed. If a machine has failed, it knows that that machine has failed. This is exactly the layer at which the failure of the stateless microservice was determined by the system so that it could determine, oh, a machine died, so I need to really figure out something, has to do something with it, and that's how we figured it out and moved it. Obviously, that's not enough for stateful, but at least for stateless, that's good enough. How does the system actually detect these failures? I think in our system, and I'm giving a fairly high level, every machine has an identity, and there's a bunch of machines. Because every machine has an identity, there's a set of machines that are considered neighbors. In this particular slide, at time t0, we have 4 machines, 5 machines, and the neighbors are 83, 76, 64, 50, and 46. At time t1, few things happened. The system is very dynamic. I mean, there is nothing that you can control here. 2 nodes failed, which is 76 and 64, and 61 arrived. I can show you that as this thing is happening, the system is under churn. It is not that there is no static knowledge in the system. The system doesn't have, there's one place where it is maintaining membership. It is all a distributed system. You can go and ask this machine, tell me, whether this machine is up. It comes back and answers it by not doing a lookup table on something, but by actually doing some distributed systems work underneath to go and tell you, yeah, that machine does exist, and it is indeed up. So after a bunch of protocols, which is multi-round protocols, it actually comes back and says, I have now figured out that machine 76 and 64 have failed, and a new machine 61 has joined. And there may be no one looking for these machines, assuming that they were already deactivated, because I'll talk about in machine lifecycle management in our system. But if these machines have failed, like in the case of stateless microservice, here is the layer at which we detected those machine failures, and the rest of the system reacted to that. Okay, so what's exactly running in our cluster? Obviously, the services that our users have written, our customers have written, our workloads have written, but there's a bunch of system services also running, and many of these are stateful. In fact, all of them are stateful. There's a failover manager service, which is actually watching every microservice that has been provisioned and running in the cluster and seeing, hey, is it up, is it running, is it healthy, and when it detects failures, it is the one which is causing failovers to happen. There's a cluster manager service which is watching, which is doing lifecycle management operations. Whenever you want to upgrade a cluster manager, it is the one that comes into play and says, okay, that it is the one that carries out those lifecycle management operations. Naming, I already talked about it. Every microservice has a name, and you want to really locate its endpoint dynamically at runtime, and you want the damn thing to scale because there's so many requests coming in the system that naming is the one where those things are happening. And image store is where every time you provision a piece of code or config or data into the system, image store service is where we actually store all that data. It's all these services are replicated. All the state is never lost unless the entire cluster goes down. And as I said, in the case of Cortana, these clusters are actually spanning 3 data centers, or whatever data centers that you want. In Cortana case, they are spanning 3 data centers. I can, Vipul, which is fine.
8.
You can actually see, just to show you guys that these services are indeed running on your scale minimized development box. You can see that there's a failover manager service running, there's a cluster manager, there's an image store, and bunch of naming service. By the way, because naming service is also partition. I'm going to talk about for scaling out partitions. So you can actually take a microservice, and not only can you say, I want n copies of that running, you can also say, I want to partition it, so that partition it by range, partition it by name, or whatever scheme that you like, so that in the case of naming service, you can see that there are multiple partitions. In this case, there are 3 partitions that are actually running. So that's basically I wanted to show you guys, the Service Fabric Explorer. That's actually part of the system. It ships as part of the SDK, so you guys can fire it up and, visualize your clusters. Okay, so So far, we talked about failures, we talked about stateless microservices. Now is the time for us to really think about how do we do state. And that's where the reliability subsystem comes in, and it is the one that is taking care of the state aspects in the system. Why are stateful microservices important? And I'm pretty sure, I think, many of us who have worked in the past have seen this particular pattern repeat multiple times. You basically start off, you take your app and you try to build it in tiers. You start with the front end, then you go and put all your business logic in this mid-tier, and you say it's stateless. And because these mid-tier can collapse any time, you go and put all your hardened state in backend databases. Then you start thinking, oh, what happens if I want reliable communication between my front end and my mid-tier? What do? I will introduce a bunch of queues. So I put it into the queue on the front end. I retrieve it from the queue on the mid-tier. Now you say, oh, I want communication, reliable communication between my mid-tier components. Oh, now let me go and put another queue between those guys. Then you come back and say, oh, I really need to think about my databases cannot really perform, my reads are slow, my writes are slow. Let me put a caching layer. Oh, now you put your caching layer. Now you say, oh, I have partition system, I have caching layers, I can't think about transactions. Let me actually try to manage all these transactions and somehow hope that my system is consistent. This is what we all faced, and this is where the system comes into play. And it is a very complex system. I can't even reason about the correctness of this system. If you go and ask any computer science guy would tell you, hey, are transactions consistent? Oh, maybe this failure doesn't happen, that failure doesn't happen, it's consistent. But that is never the case. In data center, bad things happen. And we have seen awful things happen to us many, many times. So it is important for us to really think, how can we simplify this architecture that we are all familiar with, we are all grew up with, to something that is more cogent, more simpler, and easy to understand, at the same time guarantees the correctness that we all want to have. And there comes in stateful microservices. In this world, I think you can see that it becomes much simpler. You basically have your front end. In fact, in some cases, you can avoid the front end, but because you don't need, your stateful microservice can actually terminate internet requests itself. But let's assume that you have a terminating front end that is terminating internet protocols, and then it goes and talks to a stateful microservice. In this particular case, your code is right next to that state. Of course, you have partitioned it, and I'll talk about distributed transactions down the line, but not in this talk. But the point I'm trying to say is that now you have state right next to your code, and you can now use all your reads are have very low latency. And your writes are very, very fast, and partitions are first class. And I don't know how many of you guys have actually gone and I'm sure you guys have seen what Mark actually showed. We have transactions built into the system. You can actually fault in different data structures in our system and use transactions to do updates on those transactions. So you are really writing code that you're familiar with when you're writing any mid-tier, what you used to call business logic code, where you fault in a bunch of data structures and you go and do a bunch of updates, and then you go and put it in the database. Now you no longer have to think about it like that. You just say, hey, I want to do fault in a bunch of data structures. Let me use my transaction, update all these data structures, and then if I commit, it will always stay committed. And if I abort, it will get aborted. If a failure happens, the system automatically takes care of the abort for you, and then the system proceeds. With this, the architecture becomes very, very simple. You no longer have so many moving parts. You are now, your OLTP part, the most important critical internet-facing part of your system, has best performance, high throughput and low latency. And your analytics parts of the system, where you actually periodically dump data to go into append-only stores, and so that you can do other analytical jobs on it, like MapReduce jobs, you can do that later. This is how I think the modern cloud-native app development happens. This is what we believe in Service Fabric world will happen down the line. If not now, it will happen as time passes. OK, so we actually already talked about the stateless. We showed a visual object which is moving in the space, which has state. but that state got lost when we killed the machine on which it was running. Now we will make the same stateless object stateful, and we will see how the state survives if we kill.
Okay. So this particle is represented by a stateful application. You can see that it has a primary and secondary, which Gopal will talk about.
Oh, sorry, just 5.
8, sorry.
Sorry.
Okay, so this first tab was the one that we saw, the stateless. This is the stateful microservice. This stateful microservice, you can see that the primary of this service is running on node 1. And what I'm going to do is that I'll go look at code node 1. Go into stateful service, figure out which code it is.
Can you pause there? So you guys can see that this is how the code gets run in the system. All the code, all the microservices code is sitting in a bunch of code packages, which may be running inside job objects or containers. But we know exactly which microservice is running in which code package, whether it's up or down, the machine on which it's running, whether it's healthy or not, so that we can we can make sure that the system is running healthy all the time. And
okay, so I'm going to go ahead and kill the primary process. Look what happens here in this region, as well as look what happens to the object.
So there, you can see that compared to what happened with the stateless microservice, obviously I think because it was like an entire machine going down, here the system flipped over very, very fast. Because when we are building stateful microservices, we are not actually talking about doing recovery, or you go and throw this damn thing into some external state and you resurrect that state somewhere else. In some cases, like in the case of SQL database, you have gigabytes, in some cases tens of gigabytes or hundreds of gigabytes of data. If you do recovery, you will sit there for 30 minutes before this thing happens. So how does SQL guarantee these things? Because it has these hot standbys. You just saw a hot standby in action. The instantaneous failover of the system is because all the other databases are all the data up and recovered and running, and they're just doing very simple operations. They're just applying mutations. So they're not actually consuming that much CPU, and they are actually working. And when the failover happens, they just take over. And that's how we build these systems, and that's the beauty of stateful microservices. You get that latency characteristics, you get those nice failure characteristics, and you get a whole bunch of simplicity by building around these concepts. Oh, that's the demo of stateful microservice. Doing time. Okay, so how did we actually do this? Actually, in fact, you have seen in Service Fabric Explorer, we maintain replicas of every stateful microservice. We maintain a replica set, and we have this distinguished replica called the primary replica, which is actually the one which is receiving client operations. And it is the one which is figuring if there is a read, I'll talk about that. And it is the one which is applying these state mutations. It is linearizing these state mutations for you guys who are thinking about computer science. It's and applying them in order on other places. And we actually maintain read-write quorum. So it is, we are extremely tail tolerant. I mean, there's another aspect of stateful microservice. I don't know whether I have time to go through it. The issue is tail tolerance. How many of your requests at 99.99 percentile are actually terminating within an extremely low latency? And you really need to really think about it. If in the three-tier architecture I showed, where every request has to go and talk, even if individual layers or individual components of those layers actually have 99.99 reliability, the overall system, if you compose them together, you multiply 99.99 3 times, you get 99.72 or something like that. So you're less. People think that, oh, I have a really great system, but you really have to build tail-tolerant systems. In order to build tail-tolerant system, again, it goes back to building these quorums. And the system is actually doing all of this grunge work underneath for you when you just basically did, hey, I faulted my data structure, I did a transaction, and all of this stuff is right in your code. It's regular Turing complete code. It could be C code, C++ code, C# code, or Java code, or whatever we think we can come up with. But you are writing Turing complete logic in your favorite language, using your favorite framework, and the system is doing the underlying grunge work to take care of your needs. This is a straightforward microservice in action. The system has obviously so far in this talk, I've talked about single instance microservices, whether they're stateless or stateful. But obviously, the system runs at a much, much higher density than that. So if you go back, SQL has 1.2 million databases running on hundreds of thousands of machines and tens of thousands of machines. There are hundreds of thousands of processes running on those machines. And the system is watching, carrying out, looking at taking care of failovers of every individual database with that 99.99 latency that reliability that we promise to our customers. The system is built to go and deal at that level. Now, as you can see that there are multiple replicas, and as just like I showed in the case of system services, where the cluster has multiple stateful microservices, and they are all replicating to their cohorts, some other part of the cluster. This is how the system works. I'm giving you a little peek, but I will also show you something else on how the cluster actually gets visualized. So what happens when a primary replica receives a request from its client? Let's assume that it's only doing a read. When it's doing a read, it just can service its reads. It doesn't even talk to its secondary replicas. Many people will talk about, oh, there is primary, secondary quorum. So what we are building, these replicated state machines we are building, are slightly different from what you would know about Paxos machines are. Because here there is a distinguished replica because we want reads to dominate. Because reads dominate in any microservice compared to writes, and you want reads. If you have 80% reads or 70% reads or 50% reads, you want those reads to be satisfied very fast, and you want to pay the cost in write. And if you're not careful and you don't have distinguished replicas, you will not be able to service the reads. And so that's what the system actually guarantees. There's a whole bunch of details here, but when a write happens as opposed to a read, the primary actually figures, the transaction commits, and we figure out what has all been updated. We update we send those writes to secondaries. Those secondaries come back, and when they acknowledge a quorum of them, we actually commit the transaction on the primary, and then we respond back. And then, the client generates an act. The service generates an act to its client. If one of the secondaries is slow, it may acknowledge a little later. The system realizes that the transaction is already committed, and it will do nothing with that. So this is how the system is very efficient with its reads. It's doing the best it can on the writes, and it's tail tolerant, and it's extremely scalable. Now, in this thing, this is all wonderful and great. And if I give you a probability of machine failures, and if you don't do anything with this replica set, all these replicas will die. So it's not enough for you to just do quorums and replication and other things. You need to really take care of failures that happen while these things are happening, and that is this slide. We have to reconfigure these replica sets. Just like we showed in the case of stateful microservice, we killed a primary, and the system actually reacted and promoted one of the secondaries as a primary. The way it did it is, it detected that the primary failed, it elected a new primary, and voila, the system is up and running, albeit at a reduced replication factor. In this particular case, we wanted 5. We are running with 4. And what happens is that, let's say that replica that died, it came back while it's happening, another secondary died. Then the system says, oh, it's a secondary that died. It again downshifts to a reduced replication factor for a temporary thing. These are all configurable knobs in the system, and then starts running. In the meantime, one of the primary that died comes back into the system. We detect that, the system detects that this particular replica was a primary, but it is fairly caught up. It's fairly close to what is the state in the current system without this before it died. It catches up whatever state updates that particular old primary failed and makes it the secondary. Now we are back to 4 replication factor. And if it sees that there's something called replica restart wait duration, and if that timer passes, which is configurable, the system says, okay, I'm not going to get another replica into the system. Let me go and build a brand new replica. It builds it on the side, catches that guy up, and then when it's fairly caught up, it brings it into the replica set. Now we are back to 5, replication factor of 5. And obviously, all of these things, I'm showing a nice animation, but the real system, these things, while you're doing a primary election, the new primary may die. While you're doing a secondary, another primary may die. There are lots of bad things the system can happen in the system. So building this thing is not for faint of the heart. You really think, and it's not that these are hard. Obviously, if we put our mind to anything, we can go and solve these problems. But do we really need to solve this problem repeatedly? Can't we leverage and stand on the shoulders of the giant, whether it's us or whether somebody else? So this is how we built Heze. We don't want to go and have every first-party service go and build these things, even though we are capable. Trust me, I think we have built enough of these things, and many of them have bugs. They don't, a bug fixed in one service doesn't make it to the other one. So we actually ended up building Service Fabric to go and solve these problems once for all. And we have been running this for 5 years, and now is the time for us to really make it broadly available. Remember, I talked about a single service as a stateful microservice or stateless microservice. And again, a stateful or a microservice can be partitioned. In this particular case, I'm actually showing you guys a partitioned microservice. So when the system says, oh, I will need to create a service, you can say, I want a stateful microservice of 10 partitions, each replicated 3 times, 3-way replication. And the system will take care of all of that. In this particular case, it's creating a 4-way replicated partition of a stateful microservice. It places the first partition, places the second partition, places the third partition, and at some point, it places all the partitions that you need. Voila, and then as it's doing this, one of the machine fails. Remember, watch between the two. Look at the green partition. The green partition's primary was on the failed machine. The system reacts fast. First, the federation comes in and says, okay, this machine has failed. The system heals itself, and then comes back and says, oh, there was a primary partition, green primary partition, that was living on this failed machine. Let me go and elect one of the secondaries as the primary. See, it has done that. And it now says, oh, there were some bunch of secondaries that were running on that machine, and these orange partition and red partition are actually sending replicated operations which are going into nothing. Remember and it now says, let me stop those things. And now the system is actually fairly recovered, although it is running with a reduced replication factor in the case of some of these partitions. Now it realizes that, oh, it's running with it, and it starts building new replicas, assuming the replica restart wait duration has passed, and then it goes back. And now the system has completely healed from this machine failure. And to actually drive home the point, we will actually show you a cluster monitor of this thing running in the system, which is 8?
Yes.
You can see on the right-hand side, on the left-hand side.
So here is a stateful partition microservice, which has multiple partitions. And this is the visualization of it. Here is the cluster monitor that is showing where the primaries and secondaries are placed. So you can see here for this particular partition, the primary is here, and the two secondaries are on node 5 and node 2. On this one, the primary is on node 3, and there is a secondary on this, as well as the secondary on another node.
Yeah. So you can see that all of these things are really in the system. You can visualize these things. You can, we have explorers, we have some, some built-in services that will tell you what is running where. And
switch back to one.
Switch back. Now, so far I talked about stateless microservice, single instance stateless microservice, single instance stateful microservice, and then I talked about how you can partition them so that you can have large number of instances. And now your application, as I actually described right at the beginning, is not a single microservice. It's a bunch of microservices that you put together and deploy them together into the cluster. And that's what this particular slide is actually showing, the animation. So it first goes and places those containers and places those microservices in this. And more importantly, you can create multiple instances of this application running in the cluster. And you can do A/B testing. You can have your gold customers go to one instance of the application, which is more maintained in at a lower twitch than bleeding edge customers, where you really are doing more features and updating them faster and without affecting your gold customer. So you can actually create multiple instances of these applications running in the cluster. In fact, if you actually go and ask for an Azure database, we give you a set of databases. Those databases are really distinct from the databases in the new Azure DB compared to the databases belonging to another customer. Each customer can say, I want to upgrade my database to the later version of SQL Server, while another customer may say, I want to stay back on my code base. So we are giving all these flexibilities. We have built all these things so that you once again can take these things can be taken care of for you. Now comes the application lifecycle. So we talked about how we provide a bunch of rich runtime capabilities to microservices. In this particular case, that's not, obviously that's great, that's useful, but we also need to provide additional capabilities so that our first-party workloads are for now you guys will be able to go and do lifecycle management operations on your microservices. You want to really provision and deploy, constituent microservices. You really want to upgrade microservices without affecting other microservices and without losing any availability. You want to monitor these microservices, whether they're healthy or not. There's a built-in health system in the system, and you want, more importantly, you want to have guarantees in the system. Many times you actually by now you guys have probably realized that this is a highly consistent system. You can relax its consistency, but by default you get a highly consistent system, because without consistency it's very hard to reason the correctness. Let's say you are trying to upgrade the protocol that a particular microservice implements. In order to do that upgrade, you need to go and make sure first you go and upgrade that microservice to support both the old protocol and the new protocol, as well as upgrade its client so that they start talking new protocols. But you cannot go and remove the support for the old protocol until all its clients, which are client microservices, are also have also been upgraded. But how do you get that guarantee in the system? Again, the system comes back and says, once it has finished the guarantee, it says there is no old code running in the system. So what you do, or what we do, is do a two-phase upgrade. You actually have the old protocol, implement the new protocol, have the service support both those protocols, and then go back and do another config upgrade where you switch to using only the new protocol, and in a third upgrade you actually remove that old code. So that's how you actually can manage the life cycle of a service when it is lasting for years, in some cases tens of years, and you still want to be able to reason about this system. Oh, I know that this particular version of the code is running in the system, and I know that the system is guaranteeing to me that no older version of the code that is running. If you have hundreds of thousands of machines, you can't keep track of these things. All of these things have to be automated. So next, I'm going to show you guys the actual code behind these services. You can actually see that this visual object is actually is an actor, and it has an onActivate method. It takes its life at a random place, and it registers a timer, and when the timer fires, it actually goes and moves itself. Here is a state move. Remember, in V1 code, we are saying false to rotate. So the code is fairly simple. In the case of, there is transaction pieces, reliable services, and there is another API called reliable objects. This is the reliable objects API. You can think about, in terms of objects or reliable actors, virtual actors, and you can actually go and build your, whichever programming model you like. You can build your code on top of it. And the APIs are very simple. You get activated, you get deactivated, you have a bunch of timers that you can actually fault in as needed, or you can actually listen for client requests, and you're done. And here in this particular case, the timer is kicking in and actually updating the location of the object. And if you go to the move method, you can see that at the end, if the rotate is true, it's adding a 10-degree rotation to the object. And if you go back and, where is it? Oh, sorry. You can see that all these things are actually not rotating. So these are all running version 1 of the code. We are now going to go to version 2 of the code. Here, this is version 1. Rotate is false. Version 2, rotate is true. And we'll do an upgrade, and you will see that the system will go through the upgrade without losing availability. And at the end of the upgrade, you will see these objects rotating.
So I'm going to start the upgrade. We can watch the upgrade progress in the cluster monitor as well as in the Explorer. So I'll keep both of these here. And as Gopal mentioned, while the upgrade is happening, you will see that the system doesn't lose the state, which means that these objects that are there, they will pause momentarily and restart from the same position. Remember, the state of the object was its current location and the history. If the system were to lose the state, you would see the objects jumping all over around.
You can see that it actually went through a bunch of upgrades. It actually took a bunch of code packages down to do the upgrade. Let me switch to the other one, and we'll come back to this. This is where, this is what is happening in the system. You have a package which is already running, an application which is already running, and we want to, so this is the set of microservices running on the system, and we decided to convert the yellow one from version 1 to blue one, which is version 2, and now we want to deploy it. What the system does is it goes and carefully orchestrates upgrading each of those yellow ones without actually ever losing availability, always maintaining quorums. So all the time the writes are going through, and the system stays up all the time. And it also monitors all these upgrades so that if anything goes bad, it actually rolls it back. Yeah, so
you can see some of the objects.
So now you can see that some of these objects are rotating. You can see that one of them is actually rotating, if you can see that, as the upgrade is going through. Obviously, these upgrades, you have to be very, very careful. Remember, these are not willy-nilly, create 10 instances, create 20 instances. I can do that very easily. If it's stateless, I can easily create like hundreds of instances. When you're dealing with stateful stuff, you really have to make sure quorums are there. In some cases, obviously, these objects are simple objects, but in some cases, like databases, you have gigabytes of state. You really need to think about how you carefully orchestrate these things so that you never lose availability. This is not, in a real world, these stateful objects are very, very complex objects, and they have lots of state. It's not a demo thing that I can go and spin up like 100 instances and shut down 20 instances. When the system is balancing them, it's actually doing it very, very carefully without you actually losing the availability. When I'm doing upgrade, it's not that the most important thing for me is for it to really complete, and I want to complete it in an automatic way without me actually hand-holding it. But I want to do it in a very easy way. So now you can see that the cluster upgrade is going through, and it's bringing down more and more.
So I think we're at the last UD, and then.
And you can see that it's captured. Remember, I told you how it's going UD at a time, or upgrade domain at a time, or a failure domain. You can see that it's completed UD1, UD2, and then it's actually in the end, and now actually it's done. Is it?
It's almost done.
It's pending. So it's completed. So now you would see that all of them are actually rotating. So this is how we have built this system. And there is one other thing which I want to talk about, which is the testability. All of this is wonderful, but you know that code will always have bugs. When you write code, you want to have some amount of failures happening in the system all the time. And you can actually dial up or dial down those, the rate of those failures. So the system actually comes with a pre-built chaos service, which is actually going around and killing processes, killing machines, taking machines out, and it's doing very bad things. And you can dial, there are a variety of failures that it is causing, and you can dial them up or dial them down and ensure that your service is running bug-free most of the time. So this is how you weed out the bugs before they hit your customers. Obviously, there will be some bugs that will be there in production systems, but hopefully, by the time it hits the production, you have weeded out most of the bug, and you also have the QO service running in your production system so that you are weeding out this bug as they appear. You rather weed them sooner than later. And so you can actually deploy this service, and by the way, this is how all our services are built, and you can actually go and deploy. And in this particular slide, you can see that the testability is actually causing a bunch of failures, and as those failures are happening, let me see what I have to put on my glasses. This is the problem of switching. You can see it's deactivated code packages. It is killing machines. It's killing processes. And then as it's doing its job, the cluster visualizer will show what's happening in the system. So again, the system comes with a bunch of pre-built services. You can choose to build, deploy them. Like in this particular case, it looks like it took down the entire thing, and then the system continues to operate. That brings me to, obviously there's a lot more interesting stuff here, and brings me to the end of my talk. This is. We built this service, we built this platform, this distributed systems platform, primarily for first parties. All our first parties, use a bunch of low-level APIs in our system. We realized that, some of those APIs, most of them are native APIs. We have a bunch of kernel mode code and a bunch of code in the system. If you actually download it, it will install a bunch of kernel drivers as well. So the amount of code that these guys were using, the APIs they were using, were low-level APIs. We thought that we actually, in order to make the system more approachable, we started working about a year ago, building higher-level programming models and higher-level APIs on top of the system. The core has been baked a long, long time, but the stuff that we are building on top, these approachable programming models, our approachable APIs, and the Visual Studio integration is still work in progress. There may be some rough edges that you guys will encounter as you guys are using, but we are going to fix all of them, and and the core is baked. So it is all this higher level little things. Oh, is this parameter named right? Is it confusing? Or did it actually do the right thing? And maybe there's a bug there also. So the key is that we bake the core. We are giving you the access to these bits with a much more approachable programming model, as well as tooling integrations, where you may see some rough edges, but if you guys use it, provide us feedback, we are going to ship this even on a weekly rhythm. And we want to take you guys to production by the end of this year, if possible. So please go download the SDK, build apps on top of this, and give us the feedback, and that will help us make the system better.